And because of time constraint, so let's go for the first presentation.
So today I'm going to talk about the new bytecode set Eliot and I designed for the clock virtual machine and its Smalltalk clients Quick and Arrow. So for the one who are not aware, the clock virtual machine is a standard virtual machine for Smalltalk and Smalltalk inspired environments such as Arrow, Speak and Speak. And right now with Eliot we are working on the runtime bytecode to bytecode optimizer for the clock just-in-time compiler. And basically the optimizer depends on the bytecode set quality, and it also needs additional bytecode instruction, and that leads us to the design of the new bytecode set. So I'm going to explain a bit the context, how the bytecode is used in Smalltalk image. Then I'll talk about the challenges to design a good bytecode set, the current issue of the current bytecode set, the features of the new one, and lastly how we did switch from one bytecode set to the other one. So as most of you probably know, in a Smalltalk environment, compile methods are objects, and those are objects that are shared between the virtual machine and the image. So here is the memory representation of a compile method. On the top you see the object header, which is the header for every object in the memory that gives metadata for the virtual machine to know the size of the object and such information. Then you have the compile method header, which is specific information to tip the interpreter and the JIT compiler how to execute the method. So it specializes things such as the number of temporaries. The literal frame is here to provide access to specific objects for the method execution, such as the selector of the message sends. Then you have the bytecode zone, which is the bytecode instruction the interpreter has to interpret or the JIT compiler has to compile. And lastly, we have the source pointer to fetch the sources. So by designing a new bytecode set, basically we are editing these two parts of the compile method. So the bytecode set is type-based, and basically it's interpreted by the interpreter, compiled by the JIT compiler, and it's generated in the image by the bytecode compiler. So to design a good bytecode set, we have to face several challenges. Some of them are generic, which means they apply on all bytecode sets, and other challenges are specific to our case, which is in the to design a runtime bytecode to bytecode optimizer. So the generic challenges to design a good bytecode set is firstly to be platform independent. As you know, Faro, for example, is running on mobile and different operating system. So, for example, right now there is a trend to design a register-based bytecode set, and we didn't go into that direction because we thought it would be difficult to be portable across different processors. A bytecode set has to be compact in order to lower the memory footprint. It has to be easy to decode, both by the interpreter, the compiler. And yeah, there is this notion of backward compatibility. So some tools, like some serializer, can sometimes serialize the compile method by just keeping the bytecode. And if you change the bytecode set, then you cannot materialize anymore the compile method. So we have to discuss with all the maintainers of this kind of tool when we switch to a new bytecode set and provide a way to handle this case. So about the optimizer, so I'm not going to go into detail. There is a talk on Thursday about the work of Eliot and I on the runtime optimizer for JIT. But basically what it performs right now is inlining. So inlining consists in replacing a message sent for the body of the callee. And it also performs primitive specialization. So when you want to access to a field of an array, you want to, for example, have a specialized primitive that expects that the argument is already an integer within the bound of the object. And to be able to do that, we needed to add extra bytecode instruction. So one of them consists in inline primitive or unsafe operation. So what we call unsafe operation is, for example, this specialized add primitive that will expect the argument to be an integer in bounds of the object. We also need to have support for very large methods, because inlining merges the code of several methods, which is a very big method. It needs to be possible to access to the instance variable of other object and the receiver. And lastly, the bytecode set needs to be extendable in the sense that we want to add new optimization paths with new instruction, and we may need to add new bytecode instruction. So the current issue we have right now for our bytecode set is that large methods are not supported. So probably you have not noticed it, but if you do things like a condition, like a boolean, if true, if false, the block arguments are limited to a source code that generates 1,200 bytecode instruction. So in most cases it's enough, but in the case of bytecode manipulation, it's not enough. Then there is a few available bytes, so it's difficult to add new bytecode operations that are encoded in a few bytes. The primitive encoded right now forbids inlining, whereas we want to be able to inline primitive methods. And there is one bytecode named double extending to anything, which is just crazy. So this is a bytecode that encodes in 3 bytes, like basically it can encode almost any operation of the system. And in the virtual machine, it's sometimes complicates a bit the code with a lot of switch case to find out which operation is executed. Then immediate objects such as small integers are never encoded directly in the bytecode. They are in the literal frame, and we will save quite some memory by encoded 16-bit small integers directly in the bytecode. And lastly, the closure bytecode was adding in the end, and there was very few available bytes, which made sometimes the encoding a bit complex. So I'm not going into detail about all the new bytecode set features, so you can have a look at the paper. But basically, what we added are a prefixed instruction, so it's a specific bytecode that will extend the next instruction. So for example, if you have a jump that is encoded in 2 bytes, and the first byte tells the interpreter that it's a jump, the second byte, the distance of the jump. The distance can be encoded is up to 255 because it's encoded in a single byte, and the prefix instruction will allow to have 1 more byte, which will allow the jump to encode up to 65,000 jump of up to 65,000 instructions instead of 255. And you can have several prefixes for a bytecode, which leads that you can have a jump up to an infinite number of instructions in theory. Then we added a specific instruction for inline primitive of our unsafe operations. We try to let quite some bytes available to be able to easily add new instruction. We increase the maximum number of literal to support very large methods. Yeah, and surprisingly, with all what we did, the overall bytecode size was a bit smaller in the image by 40% seemingly. And that's probably due partly to the immediate objects that are now encoded in the bytecode. So right now we encode small integers, but in the near future with SPO we will also encode characters and floating pointers. So the new bytecode set is really easier to decode. So the bytecode instruction can be encoded in a single byte, in 2 bytes, or in 3 bytes. And we sorted all the instructions by the number of bytes encoded to simplify the interpreter and stuff like that, and especially code analysis. And then within this section, we sorted the bytecode instruction by functionality, so all the jumps are next to each other. And the closure decoding has been improved, so especially there was no bytecode to push the number of temporaries of a closure, which led to very difficult analysis and closures. Yeah. So the last thing is how to switch from a bytecode set to another one. So it's possible to convert the image with an offline converter, but it's really difficult to debug because if you did a mistake, the image will probably crash at startup, and you have no clue of what's going on. So it happens that the Coq VM can support a 2 bytecode set at the same time. So it was implemented a few years ago. And what we did is that we specify a bit in the compile method that if it's set, the virtual machine knows it has to use the other bytecode set instead of the first one. and this leads to the switch between one bytecode set to the other to be quite easy, because we can start the image with one bytecode set, recompile everything into the other one, and everything keeps running. Yeah, so to conclude, we designed a bytecode set for our runtime bytecode to bytecode optimization. So what's interesting about this work mostly is the optimizer itself. And yeah, so I will present our work that I did with Eliot on Thursday morning at 9:45 about the optimizer. Questions?
When will it be put into
the production image?
Yeah.
So the VM with the new bytecode set is getting quite stable. So I think it will be bought before Christmas in the Firewall alpha.
Did you measure the size of the new compiled method without the literal frames?
Yeah, so I measure only the bytecode zone when I said that it was 40%.
So basically, in the you measure just the red boxes, just the bytecode. Okay. So then I find it strange that by lining the literals in the bytecode, you obtain a smaller bytecode.
Okay.
Because the literals
well,
are outside and...
Because you are replacing, for example, push literal n with push n as a small integer. So it tends to come out in the wash. There are many small integers. Dan's original bytecode set, which this is, encoded 0, 1, and 2. Right? But we consider, we encode in 2 bytes minus 127 to 128. Right, and then with extension bytes we can go more. So that sequence is likely the same length as fetching something from the literals. And I expect if you measure like the entire system, there's even more. I'm surprised that there's a 40% saving. That's really great.
Yeah, I was surprised.
But prefixes basically work great. Because, and the other thing to note about prefixes is that in a bytecode set, typically the 1 byte codes are not extensible. These encode the operations that have high dynamic frequency, and extensions only apply to the secondary byte codes, which are coded with larger ranges. So in the interpreter, there's very little overhead, right? Because those larger ones have lower dynamic frequency.
Okay, cool.
How do you debug when you are developing how do you work?
Okay, so there is 2 things for the bytecode set. There is the in-image compiler and the VM support. The VM support was done by Eliot and basically debugs with the VM simulator. And about the compiler, well, you just have a suite of tests.
And because context is an interpreter, right? You can compile the new bytecode set and run little simulations asking context to interpret for you, right? Hitting bugs, right? So the simulator and that both the thing about the simulator is that you're simulating the entire image as opposed to with context having to set up some small subset. That's straightforward.
Okay, so you spoke about extension. I know nothing about what kind of extension you spoke about optimization, new optimization. What is the idea there?
New optimization, you mean the runtime optimizer?
You spoke about one of the goal was to be for the game was to be extendable.
Yeah.
What kind of extension do you do?
So basically, we wanted to encode new bytecode instruction, and these bytecode instructions are not used by default by the bytecode compiler, but they will be used only by the runtime optimizer that optimize from combine method to an optimized combine method. optimize method has access to the full bytecode set to encode unsafe operation, such as the specialized height I tried to describe. And it also can have access to some specific bytecode for upwards. So when you inline, it's based on the on a statistical approach. So maybe the approach is incorrect later, and then you need to dynamically optimize the stack and stuff like that. And this is also included in the bytecode. Yeah.
But we'll, Clement will go into that in more detail on Thursday.
Okay.
Just a trivial question, how many bits do you have in a method header for designating bytecode set?
One.
How many? One bit.
Yeah, and so now that we've done this, we actually have 2 unused bits. So we could go to like Smalltalk X, which uses 2. So we could go to 4, but right now we only need the 1, right? Because we're not there yet. But what we had to do was move the primitive number out, because that was 9 or 10 bits, and that left only 8 bits for the number of literals, right? And so the change is to have a call primitive bytecode, which has the primitive number in call bytecode, and there are very few primitives in the system, so it's much more space efficient. Right?
And in addition, it allows us to use this call primitive bytecode for inline primitives.
When you say optimize, well, okay, you would say the optimize in terms of metrics of the bytecode itself, like for example the size of the bytecode, and that's pretty clear. But what's even more interesting is optimizing, let's say, the speed or the dynamic properties when the bytecode is actually executed by the VM. So you're more how do I approach that depending on the execution mode, JITted or interpreted or different modes of JITting, that the meaning of optimal bytecode set could be different, right? Like for example, you can say, oh, okay, well I'm trying to optimize push 0, right? Well, I can say, oh, well, for more code density and faster decoding in on one fetch of bytecode, I can say, oh, okay, well there's a specialized bytecode which will say, push 0, return 0, right? Or you could say push 0 and then return. In an interpreter, it makes a difference, but in a JIT, it optimizes it away anyway. If your JIT is any good, how do you deal with that?
Okay, so that's a good question. So first is the first thing is that there was a difference between memory optimization and speed optimization, right? And so we try different encoding, and it happens that usually the memory difference is a few dozen or 100 kilobytes. So right now, as we have gigabytes of RAM, we do not focus on memory optimization. Okay. So now we're focusing on speed optimization, and what is true is that we do not want the same bytecode set for a fast interpreter than with a fast JIT compiler. So what we are trying to do is to speed up the execution in the case we provide the JIT compilers without slowing down the interpreter. Okay.
I have another question about the extension mechanism. Did you think about what happens? You are saying that your bytecode compiler will have some special extended bytecodes that it will use internally. Do you think about user-defined bytecodes and how me as a user, I'm sure that if I create a new bytecode, I won't collide with the bytecode used by the bytecode compiler, or do you have some user-reserved bytecodes or something?
Exactly.
Like that?
So there is there is a few bytes, like now it's I think a dozen that is available for the user.
They're specifically reserved for user and not for future extensions to...
No, they're unclaimed territory.
That's what I'm saying.
Eliot can actually...
Yeah, that's right.
It's a homesteading sort of thing.
We are all users.
Yeah.
So I use cocaine, you may use alcohol.